So this lecture in the Gravitational Electric and Magnetic Fields unit is our first on magnetic fields. We'll have 4 lectures on magnetic fields, and this one's about magnets and electromagnets. It's section 8.1 from your textbook, and this isn't a very mathy kind of section. It's more of a, you'll see a lot of multiple choice and explain questions coming from this, but and some of this will be reviewed from grade 11, but it's important stuff we need to know in order to get us into this kind of mini unit on magnetic force. So auroras, if you've been up north, you might have seen these, and we have in the north we have the Aurora Borealis, in the south we have the Aurora Australis, and this is basically an interplay between charged particles that are in the Earth's ionosphere and the Earth's magnetic field. So the reason why these occur only in the north and the south, near the poles, the magnetic poles, is because the Earth's magnetic field is stronger at that location. And what basically happens is those charged particles in the ionosphere start to collide with I think it's nitrogen and oxygen atoms that are in the air, and they give off a lot of energy, and some of that energy is given off as light. So we start to see these kind of swirly light patterns. So it's kind of an interesting phenomena that relates to electricity and magnetism, one of the many. Now, let's go back and look at what we know about magnets. So a permanent magnet, the magnetic field inside a permanent magnet is directed from south to north, and outside the magnet it's directed from north to south. So a permanent magnet, a bar magnet, if we imagine a bar magnet, will have an electric field that kind of swirls around it. If we put little iron filings, what would happen with those iron filings is they would be directed north to south outside the magnet, and anything that would happen inside the magnet is directed south to north. So these loops that are formed are always closed loops. You can imagine an infinite number of loops that are circling around and close, that they're basically directed outside the magnet north to south, inside the magnet they're directed from south to north. So here's a quick little question. It says, where is the magnetic field the strongest? And the magnetic field is the strongest at the poles. That's where the magnetic field lines would be, if we were drawing them as vectors, single vectors, they would be the longest at those points. So the magnetic field lines of a bar magnet, you may notice that they match the electric field lines of a dipole, an electric dipole. The charge the direction is from positive to negative for an electric dipole, and there is no kind of inside. So the loops that are formed, they're not really loops. They actually start and end at the positive charge, and they start at the positive charge, end at the negative charge. Then if you kind of consider it goes from positive to negative, then back from negative to positive, they kind of form loops like that. So they kind of hook around from the positive to the negative, and from the negative you have another loop that's going back to the positive, but all of them are directed towards the negative. So there's similarities in what the pattern looks like, but it's not exactly the same as a bar magnet. And we know that opposites attract and like poles repel. So just like with electric charges, opposites attract, positives attract negatives, and like charges repel. And that's the same with magnets. So we have these bar magnets here. The south attracts the north in the first image. The north repels from the north. The north attracts the south the third image, and this, the last image, the south repels from the south. So I'd like you to copy this down. Permanent magnets, all magnets have magnetic poles. Opposite poles attract, like poles repel. Magnetic field surrounds all magnets and flows from north to south outside the magnet and from south to north inside the magnet. So the Earth is a magnetic field. It's the largest magnetic field on Earth. If we were to place a compass at different points on the Earth's magnetic field, the compass needle would be aligned with the magnetic field at that point. Now, the interesting thing with Earth is that the Earth's north pole, geographically, is actually a south pole. So whereas you hear that magnets are always, or compasses point to the north, they point to the geographic north. But remember how our magnetic field lines point from south to north inside the magnet, north to south outside the magnet. If we're outside the magnet, we're pointing to the south. That means we're pointing to the south magnetic pole. The geographic pole would be in the north. So that's something else to consider. The note here is, it says the convention is we refer to the north magnetic pole as refer to Earth's south magnetic pole as its north magnetic pole. So sometimes you'll see that. It's a bit confusing, but physically what's happening is it's a south pole in the north and a north pole in the south. I hope that doesn't confuse you too much. So you might already know Earth's magnetic field affects the motion of cosmic rays. So charged particles enter the Earth's magnetic field. They're deflected and they spiral along the field lines toward the magnetic poles. This motion results in a concentration of charged particles at Earth's north and south magnetic poles. So that's why we have that Aurora Borealis and Aurora Australis, because everything's kind of deflected towards those locations. So we won't go through this much further, but one other thing to note is that the Earth's magnetic field is actually changing location. And this image isn't too great, but it kind of shows you the geographic location of the Earth's south magnetic pole, and it's kind of moving more northward, and there's the different dates that are given there. There is a possibility that at some point the Earth's magnetic pole will switch from a north pole to from a south pole to a north pole. They'll swap, and this has happened a few times in Earth's history. We don't know why it happens, or we don't know when it happens, but we're about due for a switch. It's something else you might want to research if you're curious. And here it says that the flipping of the Earth's magnetic field has been used as a theory to help explain the extinction or evolution of some species. So, what is it that causes this magnetic field for the Earth? And inside of the Earth's core, we actually have liquid metal. And that liquid metal, some of it is ionic, which means that there's an electric charge that's being generated inside of the Earth's core. That electric charge and those moving electric charges cause a magnetic field. And that magnetic field is the magnetic field we feel on the surface of the Earth. So it's that liquid metal that conducts electricity that's flowing throughout the core. That flowing causes this magnetic field outside the Earth. So there's the Earth actually has this internal electric field that, or internal electric current that's causing this magnetic field, something that people might not be too familiar with. So you can copy this slide down. And another thing that's interesting about magnetic fields is there are actually animals that they use the Earth's magnetic field. So bees, homing pigeons, dolphins, they have organs that detect magnetic field. And one of the smallest is a magnetostatic bacterium. This is an image of one, and you can kind of see those little black dots. Those are magnetite crystals that are inside the bacterium, and they actually align themselves based on the magnetic field. So it always lets that bacterium know where the Earth's magnetic field is. So how did we find this connection between electricity and magnetism? You would have learned this in grade 11, but we'll go through it again as a quick review. It was Danish physicist Hans Christian Ørsted. He was demonstrating how a wire becomes warmer when electric charge flows through it. And during his demonstration, he saw that the compass needle that was near his conductor would kind of switch direction. And it was only happening when he was turning on the current or turning off the current. And this led us to the principle of electromagnetism, that and a magnetic field can be generated by current flowing through a conductor, and an electric current can be induced in a conductor by a magnetic field. And there's other kind of aspects of that. We'll get into all those as well. But what I'd like to explain here is the right-hand rule. So it says moving charges like those in electric current produce a magnetic field. Current in a straight or other long straight conductor creates a magnetic field whose lines look like circles centered on the wire. And the closer we are to the wire, the stronger the magnetic field is. So to determine the direction of this magnetic field, we can kind of imagine grabbing onto the conductor. This is the right-hand rule for conductors. If you grab onto that conductor, your thumb would be in the direction of the current, the conventional current, and the curl of your fingers would be the direction of the magnetic field. I don't know if I like this image that's shown here, so I'm going to show you a different one that I think is a bit better. But basically, if you hold the conductor with your right hand and you put your thumb in the direction of the current, the curl of your fingers is the direction of the magnetic field. And this happens whether it's an induced current or whether it's an induced magnetic field. If we have a magnetic field and our current is cutting that magnetic field, the curl of our fingers would be the direction of the magnetic field lines. And the induced current would appear where our thumb would be. Let me just switch this off. We also have the right-hand rule for solenoids. Now, a solenoid is a coil of wire, and this coil of wire would be basically, if we wrap a conductor around in a coil, what we would essentially be doing is we would be directing the magnetic field. So rather than having just a simple magnetic field that is that is circular, we can have a magnetic field that's very strong in the center of that solenoid. And if you put your fingers around the solenoid in the direction of the electric current, your thumb would be pointing in the direction of the magnetic field. So this is the image for that. I'm going to give you one that I think is a slightly better image. Just let me get it on camera here. So this was drawn by somebody else, but it's actually pretty good. So it shows the curl of the fingers on the right, that's the current flowing through with your curl of your fingers with that, that kind of teal color arrow. And the orange arrow is the magnetic field. Physically, what this looks like is a solenoid where the current is kind of wrapped around, it's wrapping around that coil, and the magnetic field is shown coming out of that coil. So, a use of electromagnets or electromagnetism is one of the big uses is the solenoid, and these solenoids would allow us to very quickly magnetize something. We use them in large industrial electromagnets like the one shown here, and part of the way we can create a stronger electromagnet is we can create more coils around the solenoid. We can put a larger magnitude current through the solenoid, which would give us a stronger magnetic force. We can use a more magnetically permeable material for the magnetic field, and I believe those are the main ones. So here, this slide here kind of covers how do we create a how do we induce a magnetic force through electricity, and it basically explains it this way. So every moving electric charge produces a magnetic field. A straight conductor, the direction of the current, if we know the direction of the current, we can use the right-hand rule, and the curl of our fingers will tell us where the magnetic field lines will be directed. For a coiled conductor, the curl of our fingers is in the direction of the current, and your thumb would point in the direction of the magnetic field. It's actually, your thumb is pointing at the North Pole, because we run south to north inside of a magnet.